Okay, again, we've simplified this exercise in the way we've set it up, so you actually don't have to press the go button, because for whatever reason it was taking a lot longer here to do than it did in Houston. And even the coffee break wouldn't have been long enough, which is how we did it there. Now, you choose your server. Make sure you choose remote. I was practicing this demo during the break and didn't do it about 8 times. In fact, 2 or 3 times in a row. I shouldn't admit that. And then you want to choose Stuybarrow and the exercise 8. And then hit OK. So it's server, remote, Stuybarrow, exercise 8. And it should come up. The project manager is on top, so you click and so you can see the amplitude extraction from before. You see the structure map, and you end up seeing arbitrary. Just a strict. Yeah, it is an arbitrary cross section. Well, actually, it's a straight line through the data. I'm sorry, I didn't see the 1248. And you can also see the cursor tracking here as we come into and out of the Stuybarrow fault block. And you can also see the reference horizon, which is at the top reservoir as we go from one fault block into the next, which will be the one used to flatten the data. And this is normally what we end up having before we go in and do the spectral decomposition. And again, we just sort of look and make sure that these are sort of good horizons to flatten on, well picked, and without sort of a lot of little spurious jitter in it. Okay, now after we've done this, if you go over here to wavelet decomposition on the left-hand side, you can open it up and you can see what the interface is like. It's a lot like for the amplitude extraction, very close to sort of a post-stack PAL interface. You choose your data set and ranges. There's some input parameters where the defaults are fairly good. The average velocity that we talked about getting goes in here. The rest of the defaults normally work fine. You do specify what horizons you want to stratigraphically flatten to. You choose how many. And you also can choose the source, which includes landmark. The outputs can go back into either VHP or landmark, but remember, some of this navigation you aren't going to be able to do in landmark since it's not a pre-stacked data viewer. And then you hit run and it does things. For this, unfortunately, it was taking about an hour and a half here to do, and so I've decided we set things up so it's already been done. So don't hit the run button, it's been run for you. And so now we just go over here and you want to open up the other session, which is after the wavelet decomposition view or continuous wavelet transform view. Just double click on it and it should open up for you. And you'll see a couple of different things here. Let me sort of explain. This is one of those sliced maps. It ends up being at a particular time. And in fact, if I put the cursor here and move around on the map, you'll see that it shows what time the slice has been taken at here on this little frequency gather. In fact, if I put my finger on the frequency gather, you see over here on the time slice where the crosshairs are, where that frequency gather is. So I see the time, and also this is a slice taken through the spectral decomposition at the frequency indicated by that vertical line. So I see what time has been taken at, and also the frequency is shown at the crosshairs. Then if I go and take a look at over here on what the spectral decomposition and the seismic data looks like, that you can see this is the unflattened version of it. you can see where things are coming from here at that particular frequency, and you see this sort of backdrop behind the spectral decomposition. If I go over here, you can go and see about approximately what time it is, but remember that's flattening time, and so it's not exactly at the same point. And I didn't bring up here one of the flattened gathers for you. And you also see there is the spectrum before and after flattening. This is before flattening and this is after flattening. Right now, for this purpose, I'm just going to go and just keep the one that's there sort of after flattening. But I want to sort of show you a little bit about sort of this double-click synchronization. Let's say if I wanted to go over here to this little amplitude anomaly, if I wanted to see the spectral decomposition at that point, make sure you've selected that window, and then just double-click on the point that you want, and you'll see it goes and gets that spectral decomposition. You can then go over to the spectral decomposition and say, okay, this is the time I want, and ooh, this is like right in the middle of the right frequency, so I can just click right there, and it'll go get the slice at that time at that particular frequency or bed size. If I then go, let's say, over to this location again, I'll just double click in this window. Probably double clicking too much. And it'll go up and bring up the spectral decomposition at that location on the right. And so that you'll be able to go sort of back and forth between the two and end up sort of navigating that way, be able to see what sort of the optimum sort of frequencies are with that gather. So I would just go through the particular sort of exercise, and when you get down to the movie one, I'll go and give you a little tour through exactly how the movies are done. Okay? So anyway, sort of look around a bit. I'll probably give you about 5 minutes or so, and then I'll talk a little bit about how to sort of make a little movie with this, as I showed up there.
So Mike, QI Workbench has a wavelet decomp module embedded in it.
That is
right?
correct.
And that's a PHP proprietary module?
Yes, that's right. Yeah.
Have you had a chance to compare that with like the post-stack PAL version of spec decomp?
That the post-stack PAL version and spec decomp, I have not personally done that comparison. There's a very good paper by John Castagna that compares both continuous wavelet transform with post-stack PAL version and the matching pursuit version. I did not show the post-stack PAL version. I sort of described the difference between, the continuous wavelet transform and the other one, like giving an update to your prescription. If you want to take a look at the post-stack PAL version, just take off your glasses. It's a fairly marketable difference. And it's because you're using gated Fourier transforms and not wavelet methods, the last I checked. They might have gone and updated it, but if they're still using what I was familiar with, they were using gated Fourier, which is a really bad way of doing it. So, okay.
On that e-spike, geo-energy.
What's that?
The geo-energy version.
The geo-energy is fairly close to the, gets you something fairly close to the matching pursuit. They're fairly equivalent in quality. We have benchmarked that one. We've done geo-energy, we've done Castagna's, we've done our matching pursuit, continuous wavelet transform.
So it looked like, from what I'd seen earlier, that you can export that volume, wavelet decomp volume on the Landmark project, correct?
That's
correct
exactly.
binary handshake?
That's right. That's
Yeah.
right.
No digital gymnastics.
No. You just go and click the button, choose what you want to call it. The one thing is that many times we will look on it on the viewer because you have to pre-select how many volumes you take back, how many frequency volumes, and choose those volumes. And sometimes it's good to look at like these spectrums and the like in the viewer here. And we're soon, we just about have ready to roll out where you can press one button and you'll be able to take a look at the stuff in the viewer this way. And I would suggest determining what frequencies here in the viewer, and then you can go and decide to take that back, because you don't want to take one volume and then you can put 15 back. It's a data explosion. So that you normally want to just bring like 3 volumes back. And so it's good to take a closer look at it in this viewer before you decide to bring everything back into Language.
Parameter refining this way with decomp. Trivial, does it involve?
It's, I would say that it's fairly simple. The biggest thing is sort of choosing what frequencies you really care about, but that's really, you can do it, look around it, and then those are the main ones that you want. So I'd say to hit the button to do it, there are actually very few choices. We ended up setting up a default so it really worked in a fairly ubiquitous fashion. I mean, I rarely change them. I just pretty much press the button on it. I ended up going to the data set, and you end up going, and you want to tell it where you want to, which one you want to start at, and what the increment is that you want to go and sort of move through things at. And then you end up, when you go in here to Tools Movie, and you go to the automatic capture, you tell it how many times you want to step and how many things you want to capture, okay? And that's where you decide how to do it. This is sort of part of the exercise, so, you know, go in and you can sort of try it quickly.
So the units of frequency that you entered, they're the CDP.
They are the CDPT, and let me go and sort of talk about that though real quickly. That the CDPT is sort of a number, and there are sort of 15 different frequencies or bed sizes. What they correspond into meters is stored in F2, and it's actually a logarithmic scale. Even though there are 15, they're distributed logarithmically. And it happens because most of the action happens in terms of decades. It doesn't happen in terms of a linear metric. And so it makes it so that you can do, with 15 frequencies, you go over a decade and a half, and that normally covers the full seismic bandwidth. And otherwise, if you just had like every 1 hertz, you'd have to generate a lot more volumes in order to be able to do that. I can go from about 1 hertz to, you can go easily from 1 hertz to, you know, let's say 150 hertz with about 15 different frequencies, and you see that they aren't changing. The character of the spectral decomposition doesn't change a lot going between each of these, so we probably have about the right sampling.
So, you know, wavelet decomp, that's a tool to allow you to reconstruct the depositional paleo environment, right? You
Well,
know,
yeah.
Where the channels are going, crevasse splays, things like that, and faulting too, right?
Yeah, well, I think that faulting, I mean, the coherency attributes are still, I think, are a very good thing. I mean, there are ways that people have used wavelets to actually analyze discontinuities. Geoenergy has done that. We have not gone and modified ours to be effectively discontinuity enhancers. They are very good discontinuity enhancers, but I think that some of the correlation metrics I've seen are extremely good, and I haven't seen a lot of additional value sort of coming out of a wavelet decomp for that particular metric. So. But you know, they're what's that? Yeah. Yeah, well, which, so, no, that goes back to, I don't know, was it, yeah, that Mark had asked whether or not it was good at picking up volcanics. So, I mean, I think he just answered your question. Dave McConnell used the spectral decomposition to take a look at, to identify volcanoes.
So you generally flatten your data set first.
No, 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 you want to spec decomp first, because flattening the data set actually changes the frequency. So you want to take the spectral decomposition and flatten the spectral decomposition.